Okay, we will continue from where we have stopped. We look, last time I think we were looking into the inspection schedule. We said that there are two types of, three types of structures, strategy for inspection, three types of structures, class 1, class 2, class 3, and two environments, aggressive and non-aggressive. Therefore, exposure condition you can define with respect to this, and some guidelines for periodicity of structural inspection were given. Where you have class 1 structure and very aggressive, exposure condition is very aggressive, they are severe, very severe condition, there you will do every 2 years, and in between you will do actually once routine survey, next year extended survey, which means that you might use instrument also. You can plan that accordingly what you would do every 1 year. For example, a nuclear reactor structure somewhere in the coastal Gujarat or coastal Andhra Pradesh, you possibly got to see it every year. I mean Tamil Nadu, Kalpakkam for example, or somewhere on the western coast like Trombay and similar sort of thing. So, you got to see them every year, once routinely inspection schedule and then one with some instruments. So, you may have to do, like for example, crack measuring, devices to even visually observe, and today you can have used drones and things like that, wireless communication. So, therefore, one has to use all those, you can do that. While coming to not so important structures, you may superficially do not so important structure in not severe normal exposure, you can just do it or may not do anything. Somewhere you might do it once in 10 years, that sort of thing, and routine maybe once in 5 years. So, that is how one should look into. Actually, a strategy should be decided as the guideline I have given, but then these days you can do actually monitoring, complete monitoring you can do of you can, where continuous monitoring if you are doing with instruments, then the periodicity of inspection is 0, because continuously you are monitoring it. So, you can instrument it. It has actually been done in many bridges. In Europe for example, Switzerland, many of their bridges were actually instrumented with fiber optic sensing devices, which will measure the kind of deformation, and then you can relate it to other properties like strain and derived properties out of deformation. So, how it is changing seasonally over a period of time, or if there is any damage. But normally such damages would come rarely. As I said, deterioration is one of the major problem, especially when your exposure condition is very severe, and chemical sensing or sensing for distresses related to durability, that is very, very important. At the moment we have not really, nothing commercial exactly has come, although attempts are there to find out the chloride, if it is in a chloride environment, how the chloride concentration is likely to change. Might put a capsule inside the concrete and see if the chloride concentration is changing. So, one can derive a simple relationship assuming that parabolic cost growth using this kind of a curve that I showed you earlier. I showed you a curve like this earlier, right. I showed you a curve like this earlier. So, if I know how the cost will increase, right. So, how the inspection cost will increase. Supposing I know the cost of per inspection is CI as we have used earlier, cost of per inspection is CI, and with time unit inspection cost increases something like A plus B T square or some such formula. You got to know this, but this is not very easy, like inspection cost, because inspection cost will increase because of what? If you are doing number of inspection. So, if the periodicity of inspection is n per year, so per year cost would be number of inspection, I mean 1 by n square or something, 1 by n square or something like that, 1 by n square or something. So, just let me erase this off. C I into A plus B by n square, or exponentially might decrease some sort of formula you might use. We used one exponential formula earlier, a e to the power minus n I into some b n I, something like that. So, this could be your inspection cost per unit inspection, right, or yes, I mean, there is a number of inspection, actually number of emergency calls are given like this. So, inspection cost one can also increase, because number of inspection increases, it will be possibly sorry, this would be this, I think this is not correct, I mean this is not correct, this is not really correct. Basically, the inspection cost will increase, because if you increase the number of inspection. So, this is one thing, the inspection will increase, repair cost and disruption cost will reduce, you do more inspection. So, if your periodicity of inspection is number of inspection per year is n, then 1 by n is the periodicity of inspection, right, in years, and repair cost would be related to this. So, we actually earlier related repair cost to number of inspection, because we said the number of emergency calls will reduce. Here the cost would be, if you increase the inspection during the period of time, that is during 1 by n year, you might, you know, the average repair period would be basically 0 to 1 by n, because either you have to repair next or you have to repair, you know, basically this will be related to this cost will be related. But arriving at such cost is not very easy, you need some assumptions, and once you do this assumption, you can actually find out the total cost, expected repair cycle time, that is what I am saying, which will be half the inspection time. So, you know this total cost one can total cost T c one can minimize. So, d c T c by d number of inspection that we do, and we put it equals to 0, and then you can obtain an expression of T for this. I just deliberately did not want to do the derivation to this, but physically we understand, because there is, you know, we do not know, it is very difficult to find out TMR at the moment for structural scenario. For a given environment, how do you find out when the first crack will appear, because I showed you earlier the acceptable level and normally acceptable level and submissibility limit. So, that rate of deterioration prediction is not easy at the moment. Mathematical models are not there. Some empirical guideline you may have, but mathematical models, reliable mathematical models, they are not there at the moment, very few. In fact, it is not there. I would say even if they are there, they are not, you know, not verified or things like that. So, TMR, finding out TMR is relatively difficult, and CMT is the increase in maintenance cost for a delay of 1 year. So, if you delay the repair 1 year, then this is the CMT is the cost. If you delay it in 2 years, or you know, then it will increase not linearly, it will not be double of it, but it will be some square term of T. So, that is what we said, you know, parabolically increases. Using that kind of thing, you can actually derive this sort of formula. But knowing this is not very easy, it requires time. This you might know, inspection and survey cost, this you might know. So, T can be optimal inspection time can be determined in this way, but the guidelines till something mathematical is available to us, we can use those guidelines which I have given you earlier in tabular form. If you recollect, I have given you in tabular form something of this kind, something like this I have given you earlier. I am just going back again, right, I am going back again. So, this is what I gave you, inspection interval, till there is something mathematical you can use this. And for T equals to, you know, special cases T equals to 0, where you are doing continuous monitoring. But as I said, the difficulty is you can monitor some of those mechanical issues like deformation, etc., but these are not major issues in many cases. Deformation issues are not major cases. Deformation, if it is induced by some chemical changes, then it is important. Then you know, it will come to the maintenance cost. So, failure of, if you study for failure of buildings or maintenance cost of building structures, it will be mostly largely the Indian scenario will be due to river corrosion, and which is not a structural problem. So, you measure the strain deformation, you will not get anything, but somewhere the spalling of concrete would occur, because cover concrete is, you know, is spalled out because of river corrosion. Even in bridges, one looks at it, this is one of the major problems all worldwide. Number of failures because it went unattended is this. Other failures is, as I said, one can do a survey and find out, look into the net and you can find out. Major problem will be related to something of this kind. Steel bridges fatigue becomes sometime a problem. So, this is the kind of issue actually related to relevance of maintenance and inspection. So, that's what I think. I just finished discussion in the last class. I finished discussion in the last class. So, let us progress from there, right. Let us progress from there. Now, if you want to do repair of structures, is the same like maintenance. First, assessment of current condition, which I have already shown you, diagnose the causes of distress anyway, up to date assessment of degree of distress that will be required, and then once you have done that, diagnose it, quantified the amount of repair required by inspection, then you can make an estimation. If it is repair, total condition survey has to be done to find out what is the total area which is to be repaired. And once you know that, from time to time, I mean, even if you have expected that normally structural repair or repair, special repairs including repair due to corrosion and things like that, corrosion spalling or corrosion distress, that is not envisaged in design. You think that nothing will happen, but when it comes, then you have to keep a track, and if you are doing regular inspection, obviously you will keep the track and then do the repair. So, once you have done the inspection, found out the area of repair, right, and here the repair cycle of complete renovation of the structure may not be allowed, because very important structure you will do repair, but you might see what is the cost increase, and if the cost of repair is more than that is required, half the at least refurbishment or 60% of the refurbishment of the whole thing, you might do a complete renewal, as we discussed the economics earlier also. So, first you find out what is the distress and degree of distress. For example, if you know area of patch repair for river corrosion is required, then you can estimate what is the cost. So, from condition assessment you find out that, and then you can estimate the cost. And the methodology of repair, the quantum of cost will depend upon the methodology of repair you have selected. Methodologies are more or less straightforward. Let us see if we can discuss some of them if time permits. Then design, of course, the repair scheme, and it should be cost of repair comes from estimation of cost of repair. So, you got to do a condition survey to estimate the cost of repair even complete, right. So, that is what it is. So, condition survey, first diagnosis of the cost of distress, I mean cause of distress, and the cost of distress actually, that is what estimation of the cost of repair, that is what you do from a condition survey thorough. Then you can also do a little bit of what we know, prognosis. If you do not do the repair, how will it progress? Again, we do not have really good models to do that kind of thing, but statistically you can do some, provided you do periodic maintenance, I mean periodic inspection. Last year this many number were problematic or showing signs that it may become bad. This year it has increased to something more, and next year where will it go, you can find out. So, some statistics you can use. So, let us say an example, prognosis is nothing but is the projection of future course of distress. So, time dependent complete reliable degradation models are not there at the moment, and variation of degradation over time, sometime we know. For example, if I know degradation will vary with root over t to the power half, depth of carbonation for example, it varies approximately it varies with k t to the power half. Some models there, the basis is there, physical basis is also there for this model. So, what I can do is, if there are similar relationships available for other kind of distress, that also I can look into. And prognosis means I do a histogram plot, because carbonation phenomena, I think I must have mentioned that carbon dioxide from the atmosphere enters into the cover concrete, and when pH goes down below certain level, the steel may start actively corroding. That is what we call depassivation occurs. So, if I measure carbonation to cover depth, then probability of finding the number of locations depassivated would be given by this. N1 is the number of location exhibited carbonation to cover depth more than 1, N is the total number of observations I made. So, probability of finding carbonation depth exceeding the cover depth is given by N1 by N, where N1 is the number. So, if I did some here I have done at a given time, right, and then I can plot histogram. So, histogram is carbonation to cover depth at a given time, I can find out. So, N1 number, so this is the frequency. So, total this is the total number, this is the total number will be sum of this plus this plus this is the frequency diagram. In this case it is actually 1 plus 3 4 plus 11 maybe, 11 plus 4 is 15, 15 plus 6 21, 21 plus maybe 4, 25 plus 2, 27. So, out of 27 I see that carbonation to cover depth has exceeded in 4 plus 2 number of them. So, probability of finding a location carbonated on that particular time of measurements is given by this is my N1 and this whole total sum total of all f's sigma fi is equals to n. So, it would show you 28 of them are there actually. So, 6 out of 28 showed cover depth more carbonation depth more than cover depth and 22 showed less. So, my probability of finding carbonation depth exceeding is this 6 by 28. Now, supposing I know that after some 5 years of time the relationship is T to the power half. So, the carbonation to cover depth is some constant T to the power half, right. So, if this is the time I have found out, what is the time when it will become 1 for most of them, that I can each one I can find out. For example, it was 0.8 at 4 years, let us say. So, x by C, x is the carbonation depth, C is the cover depth, was let us say at 4 years was some k into T to the power half 4 to the power half. So, at 8 years or 9 years how much it would be, I can find out, because this was let us say this was 0.8 let us say. So, 0.8, just let me write it like this properly, 0.8 was x by C at the age of 4. So, 4 to the power half. At the age of 9 I want to find out how much this value will be. So, x by C is unknown to me, same k 9 to the power half. So, if I divide the ratio of x by C by 0.8 will be equals to 3 by 2. So, it will increase by 1.5 times so it will become 1.2. So, if I want to find out what is the time when x by C will be equals to 1, that I can find out, and then I can plot futuristic histogram I can plot. So, after 5 years this was the histogram, this was the histogram now, and if I have reliable model relating to time, then after 5 years or after 10 years what will be the histogram I can find out using this kind of formula if I know T relationship, right. So, corresponding probability I can calculate out, and this probability how it changes with time, then I can find out how this probability over the whole structure changes with time, I can find out. Therefore, I can find out when I should actually do, at what probability, at when the probability exceeds a certain value, I possibly must do my repair. So, in future when I should do the repair or treatment against carbonation or change the cover concrete possibly, that I can find out. So, that is what it is. Also one can use more sophisticated statistical tools like Markov processes. So, for example, I might define state 0 no passivation risk, state 1 risk depassivated at that depassivation risk. So, no depassivation risk, 2 states I can define. So, transitional probability from going to 0 to 1 state, that I can find out, and we can use Markov's process and things like that. So, one can obtain such transition matrix and actually find out future when it is. But I think I will leave it at this stage, because at the moment real data are not available to us, but you can use this. So, you can use a transition matrix assuming that condition of structure never improves without human intervention, and condition state either remains same or shift to the next state. So, that is Markovian process. One can actually use this kind of process also, and one can one can actually obtain the initial probability matrix. Because I have to, I am not, if you are interested, you have to first look at what is a Markov process, which I am not going to talk about here, but you can actually use this kind of processes as well in order to arrive at future scenario. So, I think this is the strategy for repair of inspection and repair of structural distresses. So, so we can look into this. So, one can actually, yeah, that's right, absolute probabilities after, so Markovian process also one can use.